Question 13. A real woman supports a stationary wheelbarrow by exerting an upwards force P on the handles. An upward force R from the ground acts on the wheel as shown. The center of gravity of the wheelbarrow is marked on the diagram. Okay, explain by considering moments about G, meaning the pivot is G. So every time you see the word about with something else, whatever that something else is going to be your pivot. So why is P, or why P must be less than R? Well, you're going to start by saying, because the system's in equilibrium, or because it says in the question, a stationary wheelbarrow. So because the wheelbarrow is stationary, I'm going to say the moments clockwise is equal to your moments anti-clockwise, but we'll contextualize by saying the moments due to the force from the ground R must equal the moments due to the upward force on the handles P. Okay, so I'm going to say where moment is equal to force times perpendicular distance from the pivot. And then we're going to say, because R is closer to the pivot G than P, right? This is closer to the pivot than this, but they both have the same moments. They both have the same force times distance. So because it's closer than P, it must have a larger force for it to have the same moment. It must have a larger force for it to have the same moment due to the force. Something like that. As long as you say moments clockwise is moments anti-clockwise, this has a shorter distance than to the pivot, therefore it must have a larger force, then that's what you usually say for these sort of questions. Okay, the horizontal distance between the center of the wheel and the handles is 1.5 meters. The magnitudes of P and R are as shown. That was a tongue twister. Determine the horizontal distance between the center of gravity of the wheelbarrow and the center of the wheel. So once the distance between the center of gravity, which is G here. So let's mark it somewhere in the diagram. Let's mark this as G. So once the distance between the center of gravity and the center of the wheel. So the center of the wheel is this, right? This is all the center of the wheel. So he wants this distance here. Let's label it distance X. Okay, so we're trying to work out X. And obviously we have to consider moments. It's a moments question because they're giving us forces and they've given us a distance as well. So let's start off by talking about the moments clockwise. So if this is the pivot G, then this 320 newtons force is going to apply a clockwise moment, whereas this 80 newtons force is going to apply a anti-clockwise moment. So let's start off by saying moments clockwise equals moments anti-clockwise. And then we'll define what a moment is. We're going to say moment equal to force times distance. This alone should score you some marks. And then if you plugged in any random values, you'd also get some more marks. So even if you don't know what to do, always start a moments question like this. Then let's consider what is my moments clockwise. Well, I have the force, which is 320 newtons, multiplied by the distance, which is X, so 320X. And that's equal to my counterclockwise moment, which is the force is 80 and the distance. But what's the distance from the pivot? I know the entire length is 1.5 meters. So this distance is going to be 1.5 minus X. So let me do that, multiplied by 1.5 minus X. And we need to make X the subject, so let's simplify. So 320X. Let's expand the bracket on the right. So 80 times 1.5 is 120 minus 80X. Let's take the minus 80X to the other side, which becomes plus 20X. So 320X plus 80X is equal to 120. So 400x is 120 and x is equal to 120 over 400. That will give you your distance, which is 0.3 meters. Don't forget the units. Yeah, so this is how you always answer every moment's question. Key things to consider is your force and distance have to be, these two, they have to be perpendicular because moment is force times perpendicular distance. In this question, they were perpendicular, as we could see. So there was no extra steps involved. So let's continue. A child is holding a balloon by a string as shown. The balloon contains helium gas. Helium gas is less dense than air. The child releases the balloon by letting go of the string. Before he released the balloon, it was, stationary, meaning the forces acting on it were, I would say, mg downwards, tension downwards, and of course, upthrust upwards. But this changes all of a sudden. When he lets go, there's no longer a tension force, and it begins to fly, right? That's what happens with balloons. So the child releases the balloon by letting go of the string. Calculate the resultant force on the balloon immediately after it is released. So after it is released, he's no longer holding it, so there's no longer a tension force. And let's consider the forces acting on the balloon. Of course, there will be mg downwards because gravity acts on any object with a mass in a planet. So you got mg downwards, and you have upthrust upwards. And upthrust is going to have to be, a bit larger than mg because it says the balloon, rises, I guess. So the resultant force is what it's asking for. The resultant force is going to be, let's write F-res resultant is equal to upthrust minus mg, where upthrust, so that's equal to, upthrust is equal to the density of the fluid. The fluid in this case is air, right? It's going through air, it's moving through air, and it's giving us the density of air, multiplied by the volume. And this is the volume of fluid displaced, which is the same as the volume of the object from Archimedes' principle, multiplied by G. Why? Because remember, upthrust is equal to the weight of fluid displaced. That's the definition of upthrust. And we know that weight is mg, so mass of the fluid displaced multiplied by g. And we know that the mass of the fluid from the density equation, we know mass is equal to density times volume. So the mass of the fluid is the density of the fluid times the volume of the fluid displaced multiplied by g. And remember, this is the same as the volume of the object. So let's carry on, minus mg, which is the mass of the balloon and string, multiplied by g. So let's do that. Sub in some values, 1.2. Oh, it's just 1.2, never mind. 1.2 times by, is giving us the volume as well. 5 times 10 to minus 2 times by 9.81 minus, yeah, so there were no conversions involved in this question. Times by 9.81. That's my calculator. My hands are freezing. Yeah, so I got 0.498. So 0.498. I'm going to have to keep it to 3 significant figures just because everything here was given in 3 significant figures. So I can write it actually as 4.98 times 10 to the minus 1 newtons because it's a force. Okay, immediately after the balloon is released, it begins to move upwards, right? Because upthrust is larger than weight. The density of the air remains constant and there is no wind. Explain how the forces acting on the balloon affect its motion as it moves upwards from the moment it is released. Keep in mind, this is a star question, meaning you could only get full marks if your points link really well. Okay, so let's create a nice structured answer. So it wants it from the moment it's released. Where the second the balloon is released, The only forces acting on it is upthrust and weight. So I'm going to write that down. As soon as the balloon is released, only upthrust and weight act on it. I could even add a little commentary that there's no air resistance yet, or there's no viscous drag yet because it's yet to move. So there's no drag. Good. Then it accelerates upwards, right? And that's because there's a resultant force. So I'm going to say that upthrust is larger than weight. I might even define upthrust because some questions you get a mark for just defining what upthrust is. Where upthrust is the weight of fluid displaced. Weight of fluid displaced. Therefore, there's a resultant force because upthrust is larger than weight, so there's going to be a resultant force. So therefore, there is a resultant force acting upwards. And you always have to talk about resultant force if you ever want to mention motion. So if something accelerates or doesn't move or is stationary or is at constant speed y, or you're going to have to talk about the resultant force before you talk about the motion. So there is a resultant force acting upwards. Therefore, it will accelerate. And we know this from Newton's second law, F equals ma. If there's a resultant force, there's acceleration. Let's say it will accelerate upwards. It's always good to specify the direction. Okay, now that it's accelerated upwards, its speed has started to increase. And when something starts to move, it's colliding with molecules and there's air resistance or viscous drag or whatever. There's some sort of drag force. So we're going to say, as it speeds up, the drag forces increase, right? Therefore, the resultant force and hence the acceleration will decrease. So as it's getting faster and faster and faster, there is now a larger force opposing its motion. So there's going to be a smaller resultant force. Because there's a smaller resultant force, there's going to be a smaller acceleration. Okay, so let's write that down. Eventually, what will happen? The forces balance out. Well, what are the forces? Well, eventually, weight is equal to upthrust plus drag, right? So plus drag or plus air resistance. So that's what happens eventually. The forces balance out, i.e. there is no resultant force. That means there will be no acceleration. We could say it has now reached terminal, or you could say maximum velocity. Right, so everything links together smoothly. I would hope to get 6 marks. Question 15. Just by looking at it, you could tell it's a SUVAC question, right? There's a projectile being launched at an angle and is giving you some displacements. A boy was throwing a ball towards a wall. The wall was 5 meters from the boy. The top of the wall was 3 meters above the point where the boy released the ball. The boy tried to throw the ball over the wall, but sometimes the ball hit the wall. Okay, so sometimes it did this rather than going above the wall. Right? Why? Either he didn't throw it with a high enough initial velocity, or perhaps the angle was too steep or too small. In one attempt, the boy threw the ball with an initial velocity of 9.7 meters per second at an angle to the horizontal of 49 degrees as shown. Show that the ball traveled the distance to the wall in about 0.8 seconds. So you want to show that it's traveled this 5 meters towards the wall in about 0.8 seconds. So it's a SUVAC question. We're going to have to use a SUVAC, and you know it's a horizontal SUVAC because it traveled 5 meters horizontally before hitting the wall. So we could write down S is equal to UT. Any sort of horizontal SUVAC for projectile motion this is the only equation you could use because there is no acceleration. So there is no half AT squared. The acceleration horizontally is 0. So let's use this. What's the time? So the time is equal to your initial velocity horizontally over your time is equal to displacement over your initial velocity horizontally. The displacement is just 5 meters horizontally, and the initial velocity horizontally, we're going to have to resolve this vector. And I know that its resultant velocity is 9.7. But with any resultant velocity that's not horizontal or not exactly vertical, there's always going to be a horizontal and a vertical component. Why? Because it's at an angle. So we could say there's a vertical component and a horizontal component for this initial velocity. We're interested in the horizontal component. I could draw this triangle out for you. So it's a right angle triangle with an angle of 49 degrees. Okay. A hypotenuse of 9.7. You want the horizontal component. And for any right angle triangle where you know the hypotenuse and you know the angle, the side opposite the angle is just the hypotenuse multiplied by sine the angle. So 9.7 times sine 49. And this is just going to be 9.7 times cosine 49 because it's adjacent to the angle. Okay, so let's consider just the horizontal component, which is 9.7 cosine 49. What we get is 5 over 9.7 cosine 49. I think I got a very weird answer, but that's probably because I'm in radians. So let me switch to degrees. 5 over 9.7 times cosine 49. So yeah, just be careful. You're always in degrees. So I got 0.786, 0.786, blah, 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 which is around 0.8 seconds. And I'm going to store this value as A, because I know I'm going to have to use it in the next question because it's a show that question. Every single show that question, you're going to have to use the answer somewhere in the future. So I'm going to store that value as A because you don't want to use rounded values. And let's look at what question B is. Question B says, deduce whether or not the ball went over the wall for this attempt. So you want to know, did the ball go over the wall or below the wall? So to do that, what we're going to do is consider what was the vertical displacement by the time it traveled 5 meters horizontally. So what was the vertical displacement at this position? If the vertical displacement was above 3, for example, like this is above 3, then it would have went over the wall. But let's say it was below 3, so I don't know, vertical displacement was like this, then of course it would have hit the wall. So we're trying to work out what is the vertical displacement 0.8 seconds later or 0.786 seconds later, because that is the time it took to travel 5 meters horizontally. And that's why it's a show that question, because we're going to have to use that time. So let's now consider the verticals to that. So I'm going to write down SUVAT. We're trying to work out what the vertical displacement is. We know the initial velocity vertically is this one here, which is 9.7 sine 49. So 9.7 sine 49. Acceleration is always minus 9.81 vertically. And the time is what we worked out in this question, which is 0.786. Well, I'm just going to write A, okay, because I stored this value in my calculator. It's just going to be a little bit easy. So that means we're left with this letter, which corresponds to this following equation. S is equal to ut plus half at squared. So let's do that. S is equal to 9.7 sine 49 multiplied by the time, which I stored in my calculator as A, plus a half times the acceleration, which is minus 9.81, multiplied by the time, which is A squared. And remember, A is just, in case you didn't know how to store it, 0.786. Okay, so I'm going to do this quickly. I got 2.72 meters. So this is my displacement. So by the time I traveled 5 meters, which was 0.8 seconds later, I would be 2.7 meters above my initial starting point here. Meaning, no, I would not have, or the ball would not have went over the wall. So let's write that down. I'm going to write down 2.72 meters is less than 3. Therefore, okay. So let's carry on. Speed skating on ice is an Olympic sport. Collisions between skaters sometimes occur. State the principle of conservation of momentum. You memorize this to be a total momentum or momenta before a collision is equal to the total after a collision. Provided, this is very important, you write this, provided there are no external forces acting on any objects involved, right? Because if there is an external force, then there's going to be work done against that force, and then that will impact the velocity of either, which will impact the momentum. So another way to say this is closed system. So provided the collision occurred in a closed system. Anyway, 2 speed skaters are skating as shown. Initially, skater B is directed behind skater A. Skater B is moving faster and collides with skater A. During the collision, skater B locks his arm around skater A so that they move forward together with a speed of 6.2 meters per second. He locks his arm around, meaning you could consider it as one object after the collision, where you combine the masses. Deduce whether momentum is conserved in this collision. Well, to know if momentum is conserved, we need to first of all work out the momentum before, and then compare it with the momentum after. So let's start with momentum before the collision. And it's going to be the momentum of skater B, which is the mass of skater B, which is 60, multiplied by the velocity of skater B, which is 7.5. Plus, now we need to work out the momentum of skater A, which is the mass of skater A, which is 65, times by the velocity of skater A, which is 5.5. So this is the total momentum before the collision. And the total momentum after the collision, well, they have stuck together. So we could consider it as one object, with the mass being the sum of their masses, which is 60 plus 65 kilograms. And the velocity is given, it says as, so they move forward together with a speed of 6.2. So after the collision, the speed was 6.2. Put both of these values in your calculator and make your comparison. Just to make this quick, I know you could do this at home. Sorry, I can't even speak anymore. And then, yeah, make a conclusion. Say, therefore, momentum is or is not conserved. Okay, now it says the kinetic energy of the 2 skaters after the collision is much less than their combined kinetic energy before the collision. So the collision is inelastic. An inelastic collision is a collision where kinetic energy is not conserved. So you've lost kinetic energy after the collision due to, most of the time, energy transfer to the surroundings. Work done against frictional forces, blah, blah, blah. Maybe work done against gravity, maybe work done against elastic, or work done in stretching a spring or compressing a spring. These are all ways where energy is transferred outside the system, so energy is not conserved. So it's an inelastic collision. Anyway, explain the decrease in kinetic energy in this collision. Well, what we could say is friction acts between the skaters when they collide. Therefore, work is done against the frictional forces. And we could say that this energy is transferred outside the system, right? And it's transferred as probably heat, right? Because when you're talking about friction, you're talking about heat. So this will give you your marks. I would say just keep in mind in this specific question, the reason it's inelastic is because work done against friction. In another question, it could be that a car collides with a wall, and as the car collides, I don't know how to draw a car, something like this. As the car collides with a wall, like the front part of the car crumples, right? And then the car compresses. So energy is now transferred to permanently deform the material, right? Or plastically deform the material. This is plastic deformation. So energy is used to change the shape. So now you've lost some of that energy after the collision. So it's for that reason it's inelastic. So just keep that in mind in case maybe that sort of question comes up. All right. Known as forams are small sea creatures with shells. When they die, they sink slowly through the seawater to form a layer at the bottom of the sea. The photograph shows a magnified view of some typical forams, whatever they are. A spherical one has a mass of 1.15 times 10 to the minus 8 kilograms, is sinking at terminal velocity in seawater. Terminal velocity tells me the forces are balanced. There is no resultant force. The upthrust due to the seawater is 4.37 times 10 to minus 8. The flow of seawater around the sinking foram is laminar. So it's spherical, it's laminar. We can use Stokes' law. It says, show that the viscous drag is 7 times 10 to minus 8. It might be tempting to just say, okay, let me use Stokes' law. So F is equal to 6 pi eta VR. But however, we don't know what this terminal velocity is. We don't know what the viscosity is. We don't even know what the radius is. So we cannot use this equation. So the second way to solve this sort of question is always to consider the force diagram. And this is very, very key when it comes to upthrust and viscous drag questions. Always consider the force diagram. So it's sinking, meaning you have weight acting downwards. And it's sinking at terminal velocity. So what are the forces up? It will be upthrust and viscous drag. And they are balanced because it's moving at terminal velocity. And we want this viscous drag F at terminal velocity. Well, at terminal velocity, weight is equal to the viscous drag plus upthrust. Let's work out the viscous drag. So viscous drag is weight minus upthrust. It's giving me the upthrust as 4.37 times 10 to minus 8. We need the weight. What was giving me the mass? And I know that the weight of your foram, I actually don't know how to pronounce this, but the weight of this is the mass times g, mg, right? So we could say that F is equal to mg minus upthrust, which is equal to 1.15 times 10 to minus 8 times by 9.81 minus upthrust given. Alhamdulillah, no need to convert any units in this question. And what you get I got a very small answer. I got 6.9 times 10 to the minus 8 newtons. It was a show that question actually. So yeah, I would have to probably add more significant figures. So 6.9115 times 10 to the minus 8 newtons, which is around 7 times 10 to the minus 8 newtons. Obviously, because it's really small, it has a really small mass, it's going to have a small drag as well, because it probably has a very small volume. Calculate the terminal velocity of this. Okay, so again, to work out the terminal velocity, what we can use now is Stokes' law, because it's giving me the viscosity and it's giving me the diameter. So I could, and I know what, so let me just write the equation. So Stokes' law is 6 pi viscosity V R. So I know what the force is from the previous question. I know the viscosity and I know the radius because I know the diameter. So I could just rearrange and say that the terminal velocity, and this terminal velocity is only the case when it's the forces are balanced. So when weight is equal to upthrust plus F, because this viscous drag that we worked out is the viscous drag at terminal velocity. Just keep that in mind. So V is equal to F over 6 pi eta R. Okay, so we'll use the unrounded value from the previous question for force, which is 6.9115. 6.9115 times 10 to the minus 8 over 6 pi Viscosity is in Pascal seconds, so I don't have to convert. 1.41 times 10 to the minus 3. And then the diameter is also in meters. So I'm going to have to do radius is diameter over 2. So we do 9.2 over 2 multiplied by 10 to the minus 4. And what we would get for the terminal velocity is something really small. I got 5.65. I make it 3 significant figures. It would be better to keep it as 2, but because it was 5.65, it was like somewhat in the middle. I'm just going to keep it as 3. So 5.65 times 10 to the minus 3 meters per second. Also, I know for a fact they're not going to mark me down for significant figures. It's a 2-mark question. Unless your significant figures is something ridiculous. So if it's not 2 or 3 sig figs, then maybe you would get marked down. As the sink deeper into the sea, the temperature of the water becomes lower. Discuss how the terminal velocity of the forearms change as they sink deeper into the sea. So we need to know how the temperature decreasing impacts the terminal velocity. But the first thing we could speak about is viscosity, because we know temperature impacts viscosity. So we're going to say a lower temperature will result in a higher viscosity, right? And because there's a higher viscosity, it's going to be larger viscous drag. So there will be a larger viscous drag force. And because there's a larger viscous drag force, we could say the forces will hence balance out faster. Another way to say this is the forearms will accelerate for a smaller time. Because it's accelerating for a smaller time, because the forces will balance out faster, its terminal velocity will therefore reduce. So that's the first thing decreasing the temperature does. Also, you should know that temperature impacts the density of the fluid. Right, because we're talking about the temperature of the water, not the temperature of your, whatever that bacteria was. Okay, so we're going to say now that as temperature decreases, the density of the fluid increases. Why? Because we know that the density is mass over volume. Well, the mass of the water can't change, right? You know that mass never changes, but the volume does, because when the temperature of something lowers, the volume decreases. Likewise, if the temperature increases, the volume increases. This is called thermal expansion. But if the volume is less, you're dividing by a smaller number, so the density has increased. So what we're going to write as the volume. So I'm going to write, therefore, because, so now we're going to talk about upthrust. Therefore, because upthrust is equal to rate of fluid displaced, which is the density of the fluid multiplied by the volume multiplied by G. I know that the density of the fluid increased. The volume doesn't change because that's basically the volume of your bacteria or whatever that was. And then G is 9.81. So these G and volume don't change, but the density increased, and therefore upthrust increased. So we're going to say since there is a larger upthrust, forces balance out faster, or the forearms accelerate for a smaller time. Exactly what we said before. Hence, the terminal velocity will reduce. So actually, both of these factors have reduced the terminal velocity.